The following KQED production was produced in high definition.
Tonight on Quest, it's taller and heavier than a 4-story building. And if you don't treat it with respect, it just may kill you. Find out about the science behind Mavericks. It's one of the world's biggest and most dangerous surfing waves, and you'll find it just north of Half Moon Bay. And meet George Smoot, winner of the 2006 Nobel Prize for Physics. He can tell you where the universe came from. Now, he's trying to figure out where it's going.
Major funding for Quest is provided by the National Science Foundation, the Gordon and Betty Moore Foundation, investing in partnerships for environmental conservation, science, and the San Francisco Bay Area. The Richard and Rhoda Goldman Foundation, celebrating more than 50 years of innovative grant-making. And the Amgen Foundation. Additional support provided by the William K. Bowes Jr. Foundation, Ann S. Bowers, the Robert Noyce Trust, the Dirk and Charlene Capsinel Foundation, and the Bedez Family Foundation.
California is famous for its picturesque coastline. Pristine waves roll onto sandy shores, and each day people flock to the beach to play in the surf. But in the waters just north of Half Moon Bay lurks an angry monster, a green-faced giant who rises from the ocean deep to devour anyone who dares to stray near. This is Mavericks.
You get near that wave, it's a catapult. I mean, it is an unbelievable amount of energy that's coming through, and every person I've seen that gets near it just comes out with their eyes bugging. It is that kind of a wave that no person is really prepared for it. Mavericks is special.
The massive waves that form on this jagged reef are some of the biggest in the world. Predicting when they will strike is as uncertain as the weather, but when it's on, big wave surfers travel from all over the globe to challenge the beast. For them, Mavericks is the Mount Everest of surfing.
It's the kind of spot that is so forbidding that even with all the attention and all the hype around it, still there's very few people that want to ride the place.
Grant Washburn of San Francisco is part of a select group of surfers with both the knowledge and skills to face these waves.
Surfers, we love the challenge, but really actually the candy, the icing is the ride. I mean, the spot, it gives you a half a mile of surfing wave, and that's unparalleled in big wave surf. So it really is like the ultimate surfing spot.
Over 30 years ago, a local surfer named Jeff Clark paddled out alone and became the first person to tackle Mavericks head-on.
You know, basically there's not a lot of guys around here that are into that kind of a challenge, and it wasn't obvious that he was not crazy.
For the next 15 years, Clark surfed Mavericks alone. Few people believed it really existed. How could there be waves that big in Northern California? It became a surf myth.
There was rumors of a spot. Most people didn't believe it. It was sort of ingrained. I mean, this was the rule. Hawaii was the king.
In 1990, Clark finally convinced some friends to go out, and the news broke. Mavericks was unleashed.
I was so shocked and scared and like in awe of what I saw. They were so much bigger than what I had been led to believe. I was like just stunned, because to me this was like the holy grail.
If you want to surf these waves, it's good to understand the science behind how they break. Waves hit the California coast all the time, but the big waves at Mavericks only happen when conditions are right. These waves began their life thousands of miles away in what's known as the wave factory of the North Pacific. Using satellite technology, meteorologists as well as surfers can now monitor the growing swell and predict when these crushing waves will strike.
The Gulf of Alaska lights up in November, December, January, and February. When I mean lights up, you get these big low pressure centers that create a big pressure gradient or a big pressure difference between high and low. That low pressure gets in close proximity to a high pressure, which is farther south, and in between the two, it starts to blow.
These powerful storms generate an enormous amount of energy that gets transferred from the air to the ocean.
The waves that surfers are interested in are waves that are caused by the interaction between the wind and the water. Wind imparts energy into the ocean, and if you have a good storm, that storm is going to transfer that energy into the ocean in the form of what we call surface wind waves.
You have three things that you need when you want big waves, and this is the best place to get them. You need wind speed, how fast it's blowing. You need fetch, which is the distance of water that the wind is blowing over, and then duration, how long the wind is blowing over that. So if you get a 60-mile-an-hour wind blowing for 4 days, over 2,000 miles of ocean, you get some pretty big waves.
The waves at Mavericks can get as big as a 4-story building. But no matter what the size is, all waves are measured by three things: the height, the period, meaning the time from crest to crest, and wavelength, or the distance between the two peaks.
A 20-second period will be 20 seconds between the height passing an area, and 20 seconds is actually a very long time, and these waves can go about 14, 15 miles an hour. So if you were to take 20 seconds, it's a huge area.
In deep water, even when the wind stops blowing, the amount of energy in the wave is fixed and conserved.
Now the energy travels, but the water itself does not. The water itself just is moving in a small circular motion. Sort of like if you play with a slinky. You know, you can take a slinky and flex it, and you can see that wave motion going up and down the slinky, but the actual metal or plastic part of the slinky is only moving a little bit.
If the wave energy below the surface reaches the bottom, the seafloor acts like a speed bump and the wave slows down. The same amount of energy then gets compressed as the wavelength decreases. The only place for that energy to go is up, and the wave height intensifies.
All of the energy for that wave will be stored between the surface and a depth that is about half the wavelength. When the ocean depth gets to about half of the wavelength, then that wave transforms into what we call a shallow water wave.
The final piece of the big wave puzzle is the underwater topography and bathymetry. As the wave encounters the bottom and rises, the potential wave energy is converted into powerful kinetic energy that finally explodes as a breaking wave.
Why is it at Mavericks you can get those really big waves right there, and then at the cove right next to it, you don't get those waves? And that really comes back to the shape of the ocean floor. Mavericks is just a bunch of rocks that sort of pop up from the ocean bottom. And so what happens is they tend to just quickly focus those waves right at that spot.
Recently, Cal State Monterey used multi-beam sonar to map the seafloor at Mavericks. This is part of the State Coastal Conservancy and National Marine Sanctuary Marine Mapping Program. This image helps illustrate how this reef creates such massive waves. When the swell approaches at just the right angle, west-northwest, the wave travels from deep water and crosses the tip of the reef. As the wave energy encounters rocks in an area surfers call the launching pad, it slows down, causing the wave to bend and rise. This process, called refraction, focuses the energy that feeds these monster waves.
If you have a reef that sticks out into the ocean, and you think about a wave coming forward, what's going to happen is that part of the wave which hits the reef first is going to slow down a little bit, and that wave out on the side is going to keep going, and it's going to look like it gets bent in a little bit. And so you're going to take a whole long piece of wave, and you're going to bend it to focus the wave energy into one spot.
As it hits this shelf at Mavericks, all of a sudden they jump up. So we've got them coming in, they're dragging, they're being focused, they're being bent right into this reef, and then they really trip on the abrupt seamount out there. And a 400-yard thick chunk of ocean just leaps out of the water, and it is like the crocodile. You're seeing the nose of the crocodile, and all of a sudden the whole thing jumps out of the water. Now, the wave is not apparent of a 60-foot wave until it hits that shelf, and then all of a sudden, whoa, it's at least twice as big as you thought it was, and it happens in about an instant.
When you talk about energy release, the most amazing thing that I've ever heard, and this is absolutely the case, when the waves get big out here and they crash onto the North American plate, they register on the UC Berkeley seismograph. It shakes the North American plate when the waves go 15, 20, 30 feet out here.
Imagine being slammed under something that can shake a continent. Big wave surfers learn early on to respect this power. While understanding the physics of big waves may help predict when mavericks will strike and how to catch a ride, if you get caught in the middle of this, all you'll be thinking about is survival.
The game can go wrong so quickly. What you're feeling is the ocean just swallowing you into this abyss, this hideous turmoil-ridden area, and you can't escape it. It's like being in quicksand or something, like you can't get away. And the feeling of that is so overpowering. Your strongest effort really has very little to do with what's going on out here. The challenge, the trick, is to run in there and catch one, steal some fire before the wrath of the gods comes down on you.
To replay the segment you've just seen in its entirety and explore additional web-only video content, visit kqed.org/quest. Later on Quest, an unseen assailant is stalking California's forests.